Okay, 11.10 is on Taylor and Maclaurin series. Right? And it's a way to derive power series. Okay, so we have a theorem. Okay, if F has a power series representation at A, that is, if f of x is equal to the sum as n equals 0 to infinity of c of n x minus a to the nth power, where x minus a is less than r, so we could calculate a radius of convergence based on that. Okay, then its coefficients are given by the formula Cn is equal to the nth derivative of f evaluated at a over n factorial. Okay. Okay, so let's write this out a little bit. The summation as n equals 0 to infinity of Cn x minus a to the nth is equal to the 0th derivative, which is just the function, over 0 factorial, x minus a to the 0th power, okay, plus f prime of a over 1 factorial times x minus a to the first power, plus f double prime of a over 2 factorial times x minus a squared plus, and this just goes on forever. Okay, dot, dot, dot. Okay, so this gives us a way to get our coefficients, which is kind of fun. Okay, the Taylor series of a function centered at A is the summation as n equals 0 to infinity of f of n of a over n factorial x minus a to the nth power, okay, which is equal to f of a. All I'm doing is taking what we have above here and simplifying it. F of a plus f prime of a times x minus a plus f double prime, oops, f double prime of a over 2 factorial. Okay. You could just put 2 if you want, but I'll put 2 factorial. Okay, and that's x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed plus, and then it just goes on forever. Okay. Okay, the Maclaurin series of a function F. I'll put the F up there too. Function F centered at 0. Okay, so this is not just centered at a value. This is centered at 0 now. Okay, gives me a little bit more concise of a series because we're letting A be 0. Okay, is centered at 0 is the summation n equals 0 to infinity of the nth derivative of evaluated at 0 over n factorial x to the nth, right? Because if a is 0, then x minus a is just x. So we get x to the nth, which is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so on and so forth. Okay. So what this allows us to do is this is very good at creating, allows for creating polynomials that approximate functions. Okay, this allows for creating polynomials that approximate functions, because sometimes a polynomial is a lot easier to work with than a function is. And the more terms we take, we get successively better and better approximations. Okay, the more terms we add, the better our approximation is. Okay. Okay, let's look at finding a Maclaurin series. Okay, find the Maclaurin series for e to the x. Okay? E to the x, the guy who is his own derivative. That's why he's very famous. Right? You don't get famous in math for doing nothing. Okay? E to the x is very famous because he is his own derivative. Very interesting. Okay? Slope of the tangent line of e to the x is e to the x. Okay, so let's get some polynomials here. Okay, we're going to use this formula right here, okay, to get us successively better and better, okay, approximation of e to the x with a polynomial equation. Okay, so let's find out what these coefficients are. Okay, so the first one is f of 0. What's f of 0? That's e to the 0, which is 1. F prime of 0. Well, what's f prime of x? What's the f prime of x? Maybe I should set it up like this. Still like that. Let's go over here to f of x equals e to the x. There we go. Now let's go over, and f prime of x is e to the x. f double prime of x is e to the x. This is always just going to be e to the x, no matter how many times, how much I do this triple prime, it's always going to be e to the x. And it will always be e to the 0 f prime, which is 1. This will always be 1. Okay, so the coefficients for all of these are 1. Okay, so f double prime of 0 equals e to the 0, which is 1. F triple prime of 0 equals e to the 0, which is 1. Okay, so they're all 1. So we could say that e to the x is equal to f of 0, which is 1, plus f prime of 1, which is 1, times x, plus f double prime of 0, which is 1, all over 2 factorial times x squared, plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus, and it just goes on forever. Okay. I could kind of rewrite this e to the x as, in terms of factorials, this would be x to the 0 power over 0 factorial. That would give me 1. This would be x to the 1st over 1 factorial. That would give me x. This is x squared over 2 factorial plus x3 over 3 factorial plus x to the 4 over 4 factorial plus dot, 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 dot. Okay, which is equal to the sum as n equals 0 to infinity of what? Of x to the n over n factorial. Okay, so we wrote that as a Maclaurin series. Oops. Okay, that's a power series for e to the x. Well, that's kind of cool. Okay, what happens if I let x equal 1? Well, then I just get an approximation for the natural exponent. So letting x equal 1, we get an ever better and better approximation, and ever, what's better? What's a better word for better and better? An ever, no, an ever more accurate? Maybe that's better. Okay, an ever more accurate approximation for E. Okay, so E would be approximately 1 plus, okay, 1 plus 1 over 2 factorial, which is just 1/2, plus 1 over 3 factorial, which is 1/6, plus, okay, 1 over 4 factorial, which is 1 over 24, plus, you just keep going it forever, and that will approximate 2.718281828 45, 90, 45, forever. Okay. So that will give me an ever increasingly more and more accurate approximation for E, for the natural exponent. It's kind of cool. Okay. Okay, T sub n of x, okay, is called the nth degree Taylor polynomial. Okay, so it's an nth degree. We can choose how many terms to go out. Are we going to get the exact value? No. Are we going to get the exact function? No, but we can choose how far to go out. And this thing's called the Taylor polynomial. Tn of x is equal to the summation as I equals 0 to n. Okay, in this case, the n is where I'm stopping, not the indices. The indices is I. Okay, of f of I, the ith derivative of a, okay, all over I factorial times x minus a to the ith power. Okay, is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus, and then this goes on, but it stops. It stops with what? It stops with the nth derivative at a over n factorial x minus a to the nth power. It stops. Okay, it cuts off right there. We just tell it how many terms we want to go out. Okay. And it's n plus 1 terms actually, because we start at 0. It's we go out to the nth power, but it ends up being n plus 1 terms. So, you know, the Taylor polynomial where n is 17 would actually give me 18 terms in the polynomial. But what is it? It's the 17th degree polynomial. Okay, it's a polynomial of order 17. Okay. So this is called the nth degree Taylor polynomial of f at a. Okay, and I have here think of it as the nth partial sum, remember S sub n, nth partial sum, okay, of the series. Right? If we let n start at 0, so keep that in mind. Okay, it would be the nth partial sum if we let n start at 0. If we it would actually be n plus 1 if we let n start at 1. So keep that in mind. Okay, R of n of x, okay, is called the remainder of the Taylor series. Okay, so that f of x is equal to t n of x plus rn of x. So it's however much we didn't catch in our Taylor polynomial. Okay, if our Taylor polynomial is just an approximate value of the function up until that point. Okay. Okay, and this is true as long as the limit as n goes to infinity of Rn of x is equal to 0. Okay, so as long as these terms are getting smaller and smaller, then this is true. Okay. Okay, Taylor's inequality okay, is as such. If the absolute value of f to the n plus 1th degree, or n plus 1 derivative of x is less than or equal to m for x minus a, which is less than or equal to some d, okay, and then the remainder, Rn of x, satisfies the inequality Rn of x, absolute value, is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 power. Okay, for x minus a is less than or equal to d. Okay, so this is kind of like the error, right? This is an error bound. So we could calculate an error bound based on okay, what we've done here. Okay, number 2. Okay, let's see what we get here. Find the Taylor series for f of x equals e to the x centered at a equals 2. Let's say this is centered at a equals 2. Okay. So what do we need? We need the formula for Taylor series. Okay, that's the summation as n equals 0 to infinity of f of the nth degree at a all over n factorial times x minus a to the nth power. Okay. So this is going to produce the 0th derivative, which is just f of a, okay, plus the first derivative, f of f prime of a times x minus a over 1 factorial, which is just 1, plus f double prime of a over 2 factorial times x minus a, okay? And so that's squared, plus, and this goes on forever. Okay, so what do we need? We need some derivatives. So if f of x is equal to e to the x, then all of the subsequent derivatives, okay, are also going to be e to the x. Okay, and so if I take f of 2, if I let a be 2, okay, then this is e squared. They're all e squared. F prime of 2 is e squared, and f double prime of 2 is e squared, and f triple prime of 2 is e squared, and it just goes all the way down, okay, to f of, you know, whatever n, but it's just going to go on forever. Okay, and so this is going to be equal to e squared plus e squared times x minus a plus e squared times x minus a. But what is a? A is 2, so let's plug that in. Minus 2, and this is e squared, okay, times x minus 2 squared all over 2 factorial plus e squared times x minus squared cubed over 3 factorial plus, and again, this just goes on forever. If we wanted to write this as a sum, we could write this as the sum of e squared times x minus 2 to the nth power all over n factorial as n equals 0 to infinity. Okay. Now, what is this doing? Well, this is approximating the function e to the x. Okay, what's approximating the function? Well, this is e to the x. E to the x is approximately, okay, it's equal to it if I go out forever, if I go out infinite number of terms. But if I stop somewhere, let's go out one more. Okay, if I stop somewhere, I put on the brakes and I go at n, whatever we decide n to be. Okay, we could go out to 11, we could go out to 100, we could go out to 1,000,000. It really doesn't matter. Okay, the further we go out, the better and better approximation we get of e to the x, of the function. Okay, so we turn the function into an approximate polynomial. Okay, let's see this in action. I think we can get a lot kind of lost in the sauce by just seeing numbers on a page and letters on a page. Not a lot of numbers, a lot of letters. Okay, and so let's go to Desmos and see what are we actually doing here. Okay, so I think it helps to see what we are doing. Okay, with our stuff. Okay, so this thing is I'm going to have y equals, not capital Y, just y equals. Okay. Y equals e to the x. Let's just do e to the x. So e to the x power raised to the x power. Boom. Okay, and there's my nice y equals e to the x curve that we are often very familiar with. I'm going to kind of get rid of that. That's our e to the x, right? That's our exponential growth curve, right? That's e to the x. Okay, so what I'm going to do is I'm going to put a point on here. I'm going to say what happens when x is 2? Where are we at when x is equal to 2? Right, I'm going to zoom out a little bit. I'm going to say when x is 2, where are we on this curve? Okay, so I'm going to say I want the point x, or let's put this point in here. 2, I don't know if this will do it. Hopefully it will. 2 comma e to the 2. E squared. Let's do the squared. Boom, nice. Okay, perfect. So there's the point that I'm wanting there. Okay, so what is this saying? It's saying, look, if I take successive terms of this thing that I've created, okay, e squared. Can I not copy and paste? Because I can't. Okay, that's not fun. So if I take and go y equals e to the second power, e to the second power, okay, and to save myself from having to write e to the second power over and over and over again, let's go back to the notes real quick. Okay, and we can see that what would happen if I factor out an e to the second power here? Couldn't I just put that in front? And I would get 1 plus x minus 2 plus x minus 2 squared over 2 factorial plus x minus 2 cubed over 3, right? Does that make sense? That I could actually factor that out, because I don't want to have to rewrite the e squared over and over and over again if I don't have to. Okay, and so this just keeps going on forever, as far as I want it to go. So this is x minus 2 to the nth over n factorial. Okay. Okay, so let's go back, and that's going to be e to the second power. Okay, but I want to now include some extra terms. Okay, so I'm going to go 1 plus x minus 2. Okay, and we can see that, I'll zoom out here in a second. Of course. Let's go back. There we go. We can see that that just creates a straight line. That's a linear line that goes through that point, and it's trying to approximate the curve here. Okay, so we need some more terms. So let's grab some more terms here. Okay, so plus 1/2. Okay, 1 divided by 2. Okay, times, because it's 1 over 2 factorial times, okay, x minus 2 squared, right? And so if we look at this now, we see, oh, well, that's a parabola that does kind of approximate things as it goes up exponentially. Okay, it's not a good approximation, and and especially before 1 here, it kind of breaks up and goes up instead of going down. Okay, so let's see what happens if we add another term, a cubic, gosh, I keep doing it, a cubic term. Okay, and so let's add 1/6, oops, 0 over, okay, plus 1/6, that's 1 over 3 factorial, times x minus 2 raised to the third power. Oh, okay, so let's try that one. We're now out. Now we have a cubic that's approximating this. Come on, stop, go away. Okay, and so what happens where we get it to hug even closer, right? That is a cubic. Okay, but it is hugging that very closely. Okay, which is kind of cool. It hugs that. We could go out further and further and further, and we could get even better and better approximations. We could have done this with at x equals 0, and that makes things really easy. If we center this at x equals 0, that's going to be e to the 0 power, which is just, which is just 1. And then we just get 1 plus x squared over 2 plus x cubed over. So if we did center this at 0, okay, so 0, 0, 1. Okay, so let's see what happens if we use the Maclaurin series. So the Maclaurin just says center this at 0 to get a really nice approximation for e to the x. And you're like, okay, so at 0, 1. Okay, where's that going to be? That's going to be down there. Okay, and then e to the e squared goes away because that's just e to the 0. Okay, and then this is 1 plus the 2 goes away, so that's just x. Okay, and then this is just going to be 1/2 x squared. We'll get rid of the minus 2. Okay, and then this is going to be, oops, this is going to be 1/6, x minus 2 goes away. And we can see that we're getting a better and better approximation. We could go out here another term to 1/24. Okay, x cubed, or x to the 4th. Okay, boom, that hugs it even nicer. Okay, and then let's do one more. Let's do 1/120, right? So plus 1/120, and then this is x to the 5th, x to the 5th. Boom, isn't that a nice approximation? Okay, that's a really nice approximation until we about -2. Once we hit -2, this really, okay, really approximates that curve really nicely. I mean, we could even go out one more term if we wanted to. Okay, I have them all memorized up to 6 factorial. After 6 factorial, it gets above come on, stop it. It gets above where I have memorized the factorials. But if we add one more here, this would be 1/720, which is my favorite trick on a skateboard. Okay, 720, and that's x to the 6th power. And so, yeah, again, it hugs that thing so nicely. It just keeps going and going and going, and it really doesn't split away from it. I mean, we're going up to 115 and beyond. It really stays really nicely hugged to that exponential curve. Okay, especially down here, it's almost identical. And just keeps getting closer and closer and closer. It just flips up and down, okay, based on whether it's an odd polynomial or an even polynomial. Okay, but it becomes very, very nice. Okay, hopefully that makes sense. Again, that's centered at 0, 0, or centered at 0. That's the Maclaurin series that we did in example 1. Okay, so this was example 1. We had already showed what example 2 looked like. It's the same curve, it's just a different polynomial. The polynomial was centered at 2 and not at x equals 2 and not x equals 0. Okay. Let's go back. Okay, number 3 is cool. It's find the Maclaurin series for sine x. Okay, for f of x equals sine x. Okay, so again, we need to do some derivatives. Okay, so f of x equals sine x. Okay, and I need to do 8 derivatives here. Okay, to really get an idea of what's going on. Okay, so let's do f prime of x, that's cosine x. F double prime of x is negative sine x. F triple prime of x is negative cosine x. And f fourth derivative of x is equal to sine x. We're back to sine x. So this kind of just oscillates, right? Goes around in a circle. And then if we do the fifth derivative, that's cosine x. We're back to cosine x. The sixth derivative is negative sine x. The seventh derivative is cosine x again, negative cosine x. And the eighth derivative, we're back to sine x. Right? We need to know, well, what happens at 0? Well, the sine of 0 is 0, so f of 0 is 0. Okay. F prime of 0 is equal to cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is 0. F triple prime of 0 is equal to negative cosine 0, which is negative 1. So this kind of oscillates. It jumps. It jumps from 0 to 1 to 0 to negative 1, and then it's going to jump to 0, and then it's going to oscillate. It's going to go 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1 forever. Okay, but let's do a few more just to convince ourselves of that. This is 0 equals sine x, right? Sine of 0. But these four are just a continuation of these four, right? So we already know what those are going to be. They're going to be 0, 1, 0, negative 1, and then the last one's going to be 0. So f to the 5th of 0 is, again, cosine x. So that's cosine of 0. F to the 6th of 0 is equal to negative sine 0. And f to the 7th derivative evaluated at 0 is equal to the negative cosine of 0. Okay, and then f 8th derivative evaluated at 0 is equal to the sine of 0 again, which is 0. Okay, and so again, we get this nice little pattern where every other term, we're going to end up with 0, and then we're going to get an alternating series. Okay, which will be interesting and nice. Okay, so let's look at the Maclaurin series. What was the Maclaurin series? The Maclaurin series was n equals 0 to infinity of f of the nth derivative evaluated at 0 over n factorial x to the nth, right? That's what that guy is. Okay, so this is going to be equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial x to the 4th, sorry, x to the 3rd. I want to put 4. The x to the 3rd. Come on, move over. X to the 3rd plus f 4th derivative evaluated at 0 over 4 factorial x to the 4th plus 5th derivative evaluated at 0 over 5 factorial x to the 5th plus, I'm going to try to squeeze some more in here, f to the 6th derivative of 0 over 6 factorial x to the 6th plus, looks like I'm only going to be able to squeeze in one more, f to the 7th derivative of 0 over 7 factorial x to the 7th. Okay, so now let's figure out, well, what are these things? Well, this guy is 0 for sine x. Okay, for sine x, this thing is equal to 0, first one. That's what we have up here. Okay, the next one is 1 times x. So that's just x. So the next one is 0 over 2 factorial. 0 over 2 factorial times x squared. Okay, plus, what's the next one? The next one is negative 1. So this is negative 1 over 3 factorial x cubed. Okay, and then what's the next one? The next one is 0 over 4 factorial x to the 4th. The next one is 1 over 5 factorial x to the 5th. The next one is 0 over 6 factorial x to the 6th. And the next one is negative 1 over 7 factorial x to the 7th. And again, we could go on forever if we wanted to. Okay, so what happens to every other term? Well, every other term gets multiplied by 0. So this is gone, this is gone, this is gone. Every term that is even is gone. And so we're only left with the odd terms. And so sine of x is equal to x plus, or oops, that's minus. Okay, it's an alternating series. Okay, alternates in sign. X minus 1/3, or 1/3, I'm going to do it like this, x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, plus, could you tell me what the next one's going to be? X to the 9th over 9 factorial, minus x to the 11th over 11 factorial, plus dot, dot, dot. What would be the nth one? This would be -1 to the nth. It's actually n plus 1th term. Okay, all over what? All over n, or 2n minus 1. I'd have to do minus 1 in this one if I want to start with 1. Okay. 2n minus 1 factorial x to the 2n minus 1. Okay, that would be my nth term. And then it just it goes on forever. Okay, so if I want to write this in summation notation, okay, then we know that sine x is equal to the summation, okay, of n equals 1 to infinity of -1 to the n plus 1 term. Okay, or you could do n minus 1. It really doesn't matter. Maybe we'll do n minus 1. Okay, so we get -1 to the 0 power, which is just 1. Okay, n minus 1 term, because I'm subtracting 1 from everything, so I might as well just keep it consistent. Okay, n minus 1, and then this is all over. This is x to the 2n minus 1 power all over 2n minus 1 factorial. Okay. So if you wanted to start from 0, you could write this starting from 0, but you'd have to change, you know, how you get your values. Okay. And so you would have to start at -1 to the nth power. You'd have to go x to the 2n plus 1, because you'd be starting at 0. You'd have to add 1. Okay, all over 2n plus 1. Okay, factorial. I think that's how they write it on the sheet that I gave you. Okay, I think. Works. Okay. Okay, so that's sine x. Sine x is approximately this. I'm going to block it like so. Okay. Because it's more helpful to us looking at the polynomial than it is looking at the summation notation. Yeah, I'm going to put in a little or there. Okay, what if we wanted to find the series for cosine?
Okay, I found this on the web for S4 cosine. Okay. Check it out.
It was series, not theory. Okay, stop it. Okay, so stupid AI. Okay, sine of x, okay, is equal to this series. Okay, and so how would we find the series for cosine x is I could actually just take the derivative of this. We could go through the whole process again, like we did here, for cosine, start with cosine, but it's a very long process. So let's shorten the process. Since we already know what the series for sine is, let's just take the derivative of sine. Okay, which is cosine. Cosine is the derivative of sine, right? Okay, so let's just take the derivative of all of these terms. Let's see what happens. The derivative of 1, or of x, is 1. The derivative of x cubed is minus 3x squared over 3 factorial. Okay, and then this is plus x to the 5th, which is 5, x to the 4th over 5 factorial, minus x to the 7th, that's going to be 7x to the 6th over 7 factorial, plus, this is going to be x to the 9th, this is 9x to the 8th over 8 factorial, minus, this is going to be 11x to the 10th over 11 factorial, plus dot, dot, dot. Okay, so now some things cancel out. Well, 3 factorial is just 1 times 2 times 3. And so the 3 cancels, and it really leaves me with 2 factorial. So this is equal to, cosine x is equal to 1 minus x squared over 2 factorial. Plus, this 5 is going to cancel with the 5 factorial, leaving me with 4 factorial. Okay, so this 5 factorial becomes a 4 factorial. Okay. This 7 cancels with the 7 factorial and becomes 6 factorial. The 9, oh, this should be 9 factorial, sorry. The 9 will cancel with the 9 factorial, which will become 8 factorial. And the 11 cancels with the 11 factorial and makes it 10 factorial. So we turned all of the evens, or all the odds, into evens. It's kind of nice. Okay, so this becomes x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. Erase, please. Over 6 factorial. Okay, plus x to the 8th over 8 factorial, minus x to the 10th over 10 factorial. Okay, plus dot, 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 dot. Okay, so that's cosine, okay, which is equal to, okay, that's the cosine, okay, which we could write in terms of n equals 0 to infinity of what? How about x to the nth over n factorial? But if we did that, we would start at 0. That's good. However, we want to double these every time. So let's do 2n and 2n. Okay, so that one's kind of nicer to write because it's even powers and not odd. And the fact that, well, we are alternating every time, right? We're alternating. Okay, so how are we going to write the alternating? This was x to the 2n over 2n factorial. Okay, what do I want to be here? I want it to be x to the, or negative 1 to the nth, because I want the first term to be positive. So that's cosine x as well. Okay, you guys feel like mathematicians yet? Okay. But if you do like this stuff, if this stuff like excites you, then you might want to be a math major. So, okay, and we're not even done yet. So there's more to go here on the cool stuff that we're going to do today. Okay. So 5. Okay, find the Maclaurin series for f of x equals 1 plus x to the k power. So this is the binomial expansion. Okay, f of x equals 1 plus x to the k power. Okay, and we can approximate this guy with a power series. Okay, so let's see how that works. If I have f of x, okay, that's 1 plus x to the kth power. If I take the derivative of that, that's going to drop the power k. K is just a constant. It's whatever, you know, k has to be a whole number. Okay, but it's whatever whole number you want it to be. And so this is going to drop that power, and it's going to go 1 plus x to the k minus 1 power. Now, could do the chain rule on this. However, it's very boring. It just ends up with 1. Okay, if I do the derivative of the outside and then the derivative of the derivative of the inside is always going to be 1. Okay, it's 0 plus 1, which is 1. So multiplying by 1 is not very exciting. Okay, so that's, so, okay, and so let's keep going for a little while. Let's do f double prime. What are we going to get? Well, we start stacking these things. This is k minus 1. K times k minus 1 times 1 plus x to the k minus 2 power. And then what's the third derivative? Again, we just keep stacking these things in front. K minus 1 times k minus 2 times 1 plus x to the k minus 3 power. And this just keeps going on forever, right? Kind of ad nauseum. Fourth derivative, this is k times k minus 1 times k minus 2 times k minus 3 times 1 plus x to the k minus 4 power. And you kind of get the idea, right? Okay, I don't mean to, you know, bore you with this stuff. Okay. Okay, so we want the Maclaurin series, though, where x is equal to 0, where we're centered, okay, centered at x equals 0. So let's plug in our 0 here for x. Well, this just becomes 1. Okay, maybe I'll write it out a little bit nicer. Okay. So f of 0, f of 0 is equal to 1 plus 0 to the kth power, but that's just 1 to the k, which is 1. Okay. F prime of 0 is equal to k times 1 plus 0 to the k minus 1 power, which is just 1 times k, so that's k. F double prime of 0 is equal to k times k minus 1 times 1 plus 0 to the k minus 2 power, which is just, the 1 plus 0 just goes to 1, and that's just going to give me k times k minus 1. So these are kind of like factorials, right? But we're starting with, k and then k minus 1 and then k minus 2, and then we're starting at k and we're going down and we're multiplying down. Okay, so we'll deal with the factorial element of this in a little bit. So let's do a couple more of these. This is k times k minus 1 times k minus 2 times 1 plus 0 to the k minus k minus 1 times k minus 2. Okay, fourth derivative is k times k minus 1 times k minus 2 times k minus 3 times 1 plus 0 to the k minus 3. This is going to be k times k minus 1 times k minus 2 times k minus 3. Okay. Okay, so let's see what happens. You know, so what would it look like if I went like n terms, right? Like we went all the way to n terms here. Okay, n derivatives. Okay, so let's do this for f of n of x. That would be k times k minus 1 times k minus 2 times k minus 3 times dot 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 times k minus what? What will be the value there? Well, it always seems like I'm doing n minus 1, right? So that would be k minus n minus 1. That's why I stop. If it's the fourth derivative, I stop, right? The fourth derivative, I stop at the third with k minus 3, right? So that would be m minus 1, and then it just will become 1 plus x to the k minus n power, right? All right. Yeah, k minus n power. 1 plus k minus n power. Right? Okay, but it really doesn't matter, the 1 plus 0, because we're going to do a Maclaurin on this, right? So the Maclaurin of this nth derivative is really just this piece of it here. It's k times k minus 1 times k minus 2 times k minus 3 times dot dot dot. Okay, that's a times dot dot dot. Okay, times k minus n minus 1, which if I distribute, that's k minus n plus 1. Okay. Okay. So again, how is this going to help me? Well, oops. Okay, it's the derivatives that are going to help me build a series. So again, what's the Maclaurin series look like? It looks like this. N equals 0 to infinity of nth derivative of x over n factorial x to the nth. That's the Maclaurin series. Okay. So what is my derivative at 0? Oh, these were evaluated at 0, right? That's at 0 from Maclaurin. Okay. What's f of 0? It's right. So this is going to be f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 over 3 factorial x cubed plus dot 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 plus go all the way to n. Okay, nth degree evaluated at 0 over n factorial x to the nth degree, and then this goes on forever after that, plus plus plus. Okay, so what's f of 0? That's 1. Okay, so we'd say 1 plus x to the nth power, or sorry, to the kth power in this case, not n, k. Okay, there we go. Thank you for letting me write. Okay, is equal to 1 plus the first derivative, which is k, plus the second derivative, which is k times k minus 1 times, I'm going to put this all over 2 factorial, okay, times x squared plus k times k minus 1 times k minus 2 all over 3 factorial, okay, all plus dot dot dot. This is going to be k times k minus 1 times k minus 2 times k minus 3 dot 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 k minus n plus 1 all over n factorial x to the nth plus dot dot dot. Okay. Okay, and so the way that I can express these coefficients, okay, I can express them, especially this one over here. Okay. The last one is in terms of factorials. Okay. I could say that this is really, this is really k factorial over n factorial. It's really over k it's all really over k minus n, right? Yeah, because the next one would be k minus n, right? Let me think about that for a second. The next one would be, this would be k minus n minus 1. And so the next one that I would have to cancel is k minus n. Yes, that's correct. Because I would get 1, 2, 3, and then this would go all the way to let's put in a minus 4. If n is 4, then that would give me minus 3, yes. And if n is, but if I just do 4, that would be the 4. Yeah, okay, that makes sense. So this is k minus n, because the next one that I would have here is k minus n. And I need to cancel that out and everything that comes after it. So that would be k minus n factorial. And then we have it over n factorial. Now this has a special formula in probability, and this is called a combination. Okay, and we write this, okay, what this is, we write this as k choose n. Out of k choose n, or it's written like this as well. It's k of c n. In your calculator, it's written like this in probability. It's out of k items, choose n of them. And how many different ways can I choose n items out of k items and arrange them in different ways? How many different combinations can I have? Okay. And so we can rewrite this thing 1 plus x to the k power as the summation as n equals 0 to k, and goes up to k or up to k values of, out of k choose n, right? Okay, of x to the nth, okay, and that's just equal to what we have here. It's 1 plus k x plus k minus times k minus 1 all over 2 factorial x squared plus, and this just goes on forever. Okay, and so we use this notation that we grab from probability, and we stick it in there, and then this is our Maclaurin series for the expansion of you know of the polynomial here. Okay. And this, what we call this is the polynomial expansion for the binomial series. So let's do that. This is the polynomial expansion for the binomial series. Okay, until we call it that. Sorry, this is a typo. This goes to infinity, I'm sorry. Yeah, I thought it was a typo. But yeah, that goes to infinity. Sure. Okay, perfect. Okay, this brings us to working with power series in a pretty unique way. So let's kind of wrap this all up in a tidy little bow. And so let's talk about a couple of these power series. Okay, e to the x was what? E to the x looked like this. It looked like 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, this goes on forever, right? This is x to the 5th. These are the Maclaurin series that I'm talking about. Okay. Okay. X to the 5th, okay, over 5 factorial plus x to the 6th over 6 factorial plus, and there's a reason I'm going out this far, x to the 7th over 7 factorial plus x to the 8th over 8 factorial plus x to the 9th over 9 factorial. Okay. Plus dot dot dot, just goes on forever. Okay, and we get better and better and better approximations for e to the x for however many terms we go out. Okay, this will just get better and better approximation of e to the x. Okay, now let's look at sine x. What was sine x? Sine x was x, okay, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. These are the odds. Okay, because sine is odd. Okay, x to the 7 over 7 factorial. Okay, plus x to the 9th over 9 factorial. Okay, that's sine, and this just goes on forever. Okay, what's cosine? Cosine is 1 minus the evens, x squared over 2 factorial, plus x to the 4 over 4 factorial, minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, plus dot dot dot. Okay, so those are our 3 common Maclaurin series. Okay, so what was noticed was some interesting things happen when we deal with imaginary numbers. Okay, So if I let e to the ix, and we plug this e to the ix, this imaginary number, the square root of -1, kind of weird, we get the following power series. We get 1 plus ix plus ix squared over 2 factorial plus ix to the third over 3 factorial plus ix to the 4 over 4 factorial plus ix to the 5th over 5 factorial plus ix to the 6th over 6 factorial plus ix to the 7th over 7 factorial plus ix to the 8th over 8 factorial plus ix to the 9th over 9 factorial. Okay. And you're like, why are you doing all this work? There's a reason. There's a reason. Okay. There's a reason. There's a big punchline coming. Okay. There's a big idea. So open your minds to the big idea because it's coming. Okay. So again, if you really like this math, you should probably be a math major. Okay. So now what do we get? Well, let's simplify this a little bit more. So this is e to the ix, 1 plus ix plus, this is I squared x squared over 2 factorial. This is plus I cubed x cubed over 3 factorial plus I to the 4th x to the 4th over 4 factorial plus I to the 5th x to the 5th over 5 factorial plus I to the 6th x to the 6th over 6 factorial plus I to the 7th x to the 7th over 7 factorial. I'm just using the properties of exponents to separate this. 8 factorial plus I to the 9th x to the 9th over 9 factorial. So now we just need to know, well, what are all these powers of I? What is I? Well, I is I. What's I squared? It's -1. Because the square root of -1 times the square root of -1 is -1. What's I cubed? It's -I. What's I to the 4th? It's I again. It's I squared times I squared, which is -1 times -1. What's I to the 5th? It's -1. It's I'm sorry, it's I. Did I do that right? No, this is 1. I'm sorry, I skipped 1. I to the 4th is -1 times -1, which is 1. Sorry. Come on. Which is, you're not hanging in there with me. Come on. Okay. So this is I to the 4th is 1. That's 1. This is I to the 5th is I. It cycles every 4. Come on. I know you can do that. I know you're good. There we go. Okay, this is I. This is I to the 6th, which is -1. I to the 7th, which is -I. And then I to the 8th, which is 1 again. And then I to the 9th, which is I. Okay, so it cycles. It cycles through. Okay, and so what happens here is as we cycle through, right, we get e to the ix is equal to 1 plus ix plus 2. A little bit too high. Okay, plus I squared. Well, what's I squared? I squared is -1. Okay, x squared over 2 factorial. And then this is plus I cubed, which is -I, times x cubed over 3 factorial, plus I to the 4th, which is just 1. So that's x to the 4th over 5 factorial, or sorry, x to the 4th over 4 factorial. And then this is plus I to the 5th, which is I, times x to the 5th over 5 factorial. And then we go to x to the 6th. I to the 6th is -1. So it's negative x to the 6th over 6 factorial, plus I to the 7th, which is -I, times x to the 7 over 7 factorial, plus I to the 8th, which is 1, times, which is +1, x to the 8th over 8 factorial. Okay, and then plus I to the 9th is I, times x to the 9th over 9 factorial. Okay, so, and this just goes on forever. Okay, so now what I'm going to do is I'm going to group everything that has an I and everything that does not have an I. So I'm going to rearrange the terms. I'm going to say that this is 1 plus, or no, not plus, sorry, 1 minus come on, I erase. Doesn't like it when I try to erase. Okay, that's fine. Just won't make any more mistakes. Okay, sorry. Sorry. Made it mad. Come on. No. Fine. I'll close the program. Hopefully I don't have to rewrite all this stuff. Try it again. See where it left off. Gosh, it did leave that off. Okay, that's fine. Okay, so frustrating. Okay, I -1, negative I, 1, I to the 5th is just I. Then it goes -1, negative I, and then 1, and then I. Okay, I to the 6th, I to the 7th, I to the 8th, I to the 9th. Okay, so we plug this in. And the idea is that we can group these, okay, this together so that e to the ix equals 1. This should be a minus. You're gonna let me subtract the ratio. Come on, dude. Oh, can I scribble it over? I don't think so. I don't think I have scribble ability unlocked. Broski, whatever. Okay. Oh, great. You erased the one that I didn't want erased. That's so lovely. Oh, there we go. Okay, finally. 1 minus, this is x squared over 2 plus x to the 4th over 4 minus x to the 6th over 6 plus x to the 8th over 8 plus ... Okay, and then all the others had an I involved. And so this was, if I factored out the I, that's involved in all these coefficients, it would be I times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9 over 9 factorial. And so what this tells me, okay, is that e to the ix can be written, okay, e to the ix can be written in terms of the power series for cosine and the power series for sine. So this can be written as cosine x, okay, plus I sine x. Okay, and this is a very famous formula called Euler's formula. Okay, which we can also derive de Moivre's formula from this that you might have seen in trigonometry. Okay, it's e to the ix equals cosine x plus I sine x. Okay, and we can get Euler's identity from this, which is kind of amazing, that if we let x equal pi, then something kind of miraculous happens. We get e to the I pi equals the cosine of pi plus I sine pi. Well, the cosine of pi is -1. So that's -1. And then the sine of pi is 0. So this is plus I times 0. So this is e to the I pi. So this is e to the I pi. If I bring the 1 over, I get plus 1 is equal to 0. And this is called Euler's identity. Okay. And it's extremely famous in mathematics because it contains the 5 most used constants in all of mathematics. So the 5 most used, or I'll just say the 5 most important constants in all of mathematics in one identity. Okay, and so the universe holds. Okay, and again, it's called Euler's identity. It's e to the I pi plus 1 is equal to 0, which is kind of amazing when you think of it. I mean, when you think of what e to the I pi is, what is I? I is the square root of -1. So what this really says is it says, if I take this number 2.718281828 goes on forever, and I raise it to the square root of -1, and I raise that to the 3.14159264 forever. If I raise these 3 really weird numbers together and I add 1 to it, I get 0. Crazy. That's crazy nuts. Okay, but we have the 5 most important constants of all time in mathematics in one identity. It's crazy stuff. So extremely famous. And again, if you liked this stuff, then maybe you should be in mathematics. Okay, and that's Euler's identity. Okay. Apologize for the technical difficulties we had there. Oh my God.